Okay, so hopefully you all can see this. If there's any technical problems, feel free to message me or unmute yourself and let me know. So typically after our quiz is due, which it was due 3 minutes ago at 1 p.m., so make sure you don't make any changes to those documents after 1 p.m. Because I'll see that in the history of the doc. I do want to go over the quiz questions with you in addition to giving you individualized feedback within your Google document, but I wanted you to see kind of a full explanation. So we'll go through these relatively quickly in the context of the lecture where they're most relevant. So here I've got two carbons. They may or may not be connected directly to one another. I've got a nitrogen. I've got 3 chlorines, so I don't really necessarily even know where the chlorines need to end up. If I put the chlorines on the wrong atoms, and then I count up all the valence electrons and try to put them in, I may find that I can't complete all the noble gas configurations, or I get some unstable formal charges, so then I have to rearrange things. So a lot of times, especially if I have lots of atoms here, there's a fair amount of trial and error involved in making sure that you eventually get to the most stable optimal structure. So I looked at a lot of your quizzes already, and most of you recognize that to make this relatively stable, if I put all 3 chlorine atoms on that carbon, then I'd count up the valence electrons. So carbon is in column 4A, and there are 2 of those. Chlorine is in column 7A, and there are 3 of those. And nitrogen is in column 5A, so that's 21, plus 8 gets me to 29, plus 5 gets me to 34 valence electrons. If I don't put the right number of valence electrons in, my structure can never be correct. So I've already used 2, 4, 6, 8, 10 to make all the bonds, so I can subtract that if I want, and then put the remaining 24 electrons in. Generally, I want to put them on the more electronegative atoms first because they naturally attract electrons better. So chlorine and nitrogen both have almost the same electronegativity, so I can put these in here: 2, 4, 6, 8, 10, 12, 14, 16, 18. So it took 18 to fill up the noble gas configurations for the chlorines. I've got 6 more. I go 2, 4, 6. That fills up the nitrogen. But as most of you recognized in your Google documents, the carbon here still does not have a complete noble gas configuration. So if I get rid of this pair and share it in there, the carbon will be closer to having 8, but still only has 2, 4, 6. So one more pair eliminated, moving in there, will complete the noble gas for all the atoms. Now I want to calculate formal charge. In this case, the formal charges all come out to 0, which is great. That's the most stable situation. If I had a bunch of unstable formal charges, I would think about how to rearrange things and make it more stable. So then the next structure, the carbon connected to the oxygen. I know that has to be the case because hydrogen can't be in between there bonded to more than one atom. Hydrogen can only have one total bond. Do I want to put the hydrogen on the oxygen or the carbon? Well, if I bond a whole bunch of things on the oxygen, more than 2 bonds, I'll start to calculate an unstable formal charge for it. So it makes more sense, since carbon is most stable when it has 4 bonds, whether they're all 4 single bonds or a triple bond and single. 4 bonds gives it 0 formal charge, and that is optimal for it. So I want to bond as many things to carbon as possible in general. Then I want to count the valence electrons, so 4 for the carbon, 1 from each hydrogen, and 6 from the oxygen gives me 12. So far I've used 2, 4, 6 to make the bonds. So I've got 6 left, just enough to complete the noble gas configuration for the oxygen, giving it 8. And this is something we, I think, mentioned last time. I want to re-emphasize. Never should you ever give hydrogen more than 1 bond, because 2 electrons total makes its noble gas configuration. And never should you ever give a second energy level atom, anything from the second row on the periodic table where the valence electrons are in the second energy level, like carbon, nitrogen, oxygen, or fluorine, those should never have more than 8, because there just isn't space in that energy level to put them there without putting them in an antibonding orbital, which is especially unstable. But the carbon here still only has 6, and it needs 8, so if I take another pair and move it in, I'll make a double bond. Now everything has complete noble gas configurations. Then I want to calculate the formal charges and double check them. We have some other examples of formal charge. We'll see how to do that. So there's the optimal Lewis structure for that one, and then this last one. Now I've got two oxygens, so I want to put them both on the carbon. I want to avoid doing oxygen-oxygen bonds as much as possible. I want to avoid highly electronegative atoms bonded to other highly electronegative atoms, unless there's no way to avoid it, because those bonds are not very stable. As both atoms are electronegative, they're both pulling those shared electrons away. Creates a lot of tension on the bond. It's easy to break, and so they don't last very long or exist much in nature. So now I've got two hydrogens, so you might think, well, I'll put these two hydrogens on here. That way carbon has all the electrons it needs for a noble gas configuration. When I count up the valence electrons, 4 from the carbon, 1 on each hydrogen, 6 on each oxygen, since oxygen's in column 6A on the periodic table. And so that gets me to 18 total. I've used 2, 4, 6, 8, so I've got 10 left. So 2, 4, 6, 8, 10.
I have a question.
Yes.
Why? Wait, if you said two electronegative atoms shouldn't be bonded to each other, then why do chlorine exist in diatomics and stuff like that? Or does it not count because it's the same electronegativity?
Well, it does count, but if you have a sample that's just elemental chlorine only, and there's no other elements around, you really have no other option, because if they're neutral and they only have 7 valence electrons, they're never going to make a noble gas configuration. So coming together and sharing a pair to make a bond is at least completes the noble gas configuration for both atoms, because both atoms have now 8 electrons around there. So it's always going to be relative. So in general, chlorine is pretty unstable. That's why we use it to disinfect pools, and that's why hydrogen peroxide is unstable. We use it as a disinfectant as well, and that's because those bonds are not very stable. They're more stable than not having noble gas configurations for the atoms, if that's the only other option in the case of a sample that only has chlorine atoms. But yeah, it's not very stable, so that bond would, if it undergoes even a mildly strong collision, the bond could break, and then I would have individual chlorine atoms without noble gas configurations, and then those would start to try to form bonds with hydrogen or carbon or something like that, and that would break down bacterial cell walls and things like that, and start to do that disinfecting action. Great question. So back to this structure here. I didn't have enough electrons to complete the noble gas configuration for this oxygen. So anytime I don't have enough on an atom, I look to the neighboring atom to see if there are any lone pairs that could just be shared in there to fix the oxygen, but there aren't. So that tells me I need a different skeletal structure. So instead of putting both hydrogens on the carbon, I'm only going to put one hydrogen on the carbon. Most of you came up with this eventually in your answers on your quizzes. And the other hydrogen should go on one of those two oxygens. Then when I put the electrons in, I still don't have enough to complete all the noble gas configurations for every atom, because the carbon still only has 6. But at least now the atom that needs more electrons to make its octet or noble gas configuration is right next to an atom that has a lone pair that can be shared in there. So you could imagine sharing that one, or you could imagine sharing the other one. So let's just draw that real quick here. So if the other oxygen, if I took that lone pair and shared it in here instead, is that reasonable? Oops. That's not good. I don't know what that does. That's reasonable. At least all the atoms have noble gas configurations. But when I calculate the formal charge, I'm going to end up with a negative on this oxygen and a positive on this oxygen. So that tells me this is not the optimal arrangement. At least this one is better, because at least all the atoms have 0 formal charge or charge balance, in addition to having complete noble gas configurations. So those were the best answers you could give for those particular quiz questions. The second quiz question about formal charge, most of you eventually got this correct within your Google documents. I'll cover a couple of these. and then show the other so you can check your work and let me know if you have questions. But let's just take a look at this nitrogen here. Nitrogen for formal charge. The formal charge formula is the number of electrons it would normally have when neutral, which depends on the column it's on the periodic table. So for nitrogen, that's 5A. So we normally have 5 valence electrons to be neutral. Well, how many are actually assigned to it? 1, 2, 3, 4, 5, 6. At least, because every lone pair electron is only on that atom. And then a 7th electron coming from the shared pair. So a shared pair of electrons, one of those electrons counts toward one atom's formal charge, and the other electron counts toward the other atom's formal charge. So the nitrogen has assigned to it 7 electrons. It should have 5 if it were neutral, but the extra 2 electrons are subtracted because they're negatively charged, leading to an overall charge of 2 minus or minus 2 for that atom. Let's take a look at this sulfur here. So this nitrogen, if you do the same formula, you would end up with a positive. Looking at the sulfur's formal charge should be equal to the normal number of electrons sulfur needs to be neutral, which is 6 because it's in column 6A, minus the number actually assigned to it. So it only has 2 all to itself. So I'm going to add this up in parentheses. I want to subtract all the electrons assigned to that sulfur. So it has 2 all to itself. And it has 3 bonds. 1 bond to the carbon, and then 2 bonds that aren't shown, but 2 bonds to 2 hydrogens. So that's 2, 4, 6 pairs of electrons shared, but since they're shared, only half of the shared electrons count toward the sulfur, the other half count toward the other atom they're being shared with. So half of the 6 shared, and so that equals 6 minus 6 minus 5. 6 minus 2 plus 3 is 6 minus 5, and so that's how I get a plus 1 for that sulfur's formal charge. This carbon here, I'm noticing, is going to have the same charge as this one here. So let's take a look at that. And that's because the formal charge for carbon, just like these other calculations, depends on the number of electrons it would need to be neutral, which is 4 for carbon because it's in column 4A on the periodic table, minus the number assigned. And so what I can see here is I don't necessarily have to calculate for every single atom in the structure, because any atoms that have that are in the same column on the periodic table and that also have the same number of bonds and lone pairs will always have the same formal charge, because, well, the formula will always work out for them the same way. So this carbon has 2 electrons it owns all to itself, and so does this one. And this carbon has 3 shared pairs, so that's 6 total that it's sharing, and so does this one. 3 shared pairs, 6 being shared. So half of those 6 being shared gives me a 4 minus 5, and so I can calculate that both of these carbons are pretty unstable because of the charge imbalance and the fact that if all they were to do would be to share that pair of electrons with another atom, then they would have 4 bonds, and it would end up being 4 minus half of 8 shared electrons, which would be 4 minus 4, or 0. So that's the optimal situation for a carbon atom. So any carbon atom that has 4 bonds and no lone pairs is going to be optimally stable with 0 charge imbalance on it. I'll take a quick look at this boron. So I'll fill some of these other ones in since we don't really have time to do every single one of them. But the boron here, the formal charge for that boron is in column 3A on the periodic table. So it would normally only have 3 electrons, or need 3 to be balanced in charge. And I would subtract from that the number assigned. It doesn't have any lone pairs, but it has 2, 4, 6, 8 shared electrons. But since they're shared, only half of them count toward the boron, the other half count toward the other atoms it's sharing them with. And so that's 3 minus 4, and that gives me a negative 1 as well. So that would be a negative charge on that boron. Any questions about any of that? All right. So then the two questions that Akuo asked to cover before a lecture relate to some of the stuff we talked about yesterday. Drawing Lewis structures, drawing multiple Lewis structures that are similarly stable. That would mean we're drawing constitutional isomers. We talked about that concept last time. So constitutional isomers involve different ways of connecting the atoms to make different structures, even though the structures are composed of the same number of each type of element. Right? So if we want to draw a Lewis structure for this, maybe there's multiple Lewis structures we can draw that all have complete noble gas configurations and all have equally stable zero formal charge or minimal formal charge, and that would be ideal. So if I've got 3 carbons, I could connect them like this. It's going to be messy. Try to erase that line. I could connect them in a row. I could connect them with the nitrogen in between. That might create a different structure. Right? So if I'm looking at constitutional isomers, I want to think about all the possible ways that these atoms could be connected differently that would lead to something stable. So I forgot to put my nitrogen in here. So I could put it on the end, or I could put it on the middle carbon, or the fourth possibility would be to put the nitrogen in the center and connect the carbons to the nitrogen. So you might say, well, in Gen Chem I learned I want the least electronegative atom in the center, not the most electronegative atom in the center. And that's a guideline that will often lead you to the most stable structure, but not necessarily and not always. So my recommendation is don't worry about that guideline too much if you're told there are multiple isomers, because you may find stable isomers where the more electronegative atom is in the center, as long as you don't end up with unnecessary formal charge for it. Right? So for nitrogen, if we are looking at the formal charge, for nitrogen to be optimal with zero formal charge or complete charge balance, since it's in column 5A on the periodic table, it would need to have 5 valence electrons shared or assigned to it. So if it has 3 bonds, that's 6 electrons, but only half of them count. So that's 3. And so 2 more in a lone pair would really optimize that nitrogen. So it doesn't have to have, nitrogen can be a central atom. Ideally you wouldn't want to give it 4 bonds because that would create a +1 formal charge for it, but 3 bonds in a lone pair is really quite stable for nitrogen, so I can do that no problem. So I also would recommend that you put the hydrogens in last, because typically the hydrogens are always going to be on the outside, and also if you're looking for differences in connectivity, usually it's the way the other atoms are connected to one another that make the differences, as you can see here in this example. If you put the hydrogens in last, they'll just help you complete the noble gas configurations. So I've got 9 hydrogens. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And when I count up the valence electrons, I'd have 2 left to fill the noble gas for the nitrogen. Over here, 1. You can get the sense that I hate drawing in hydrogens, and they're really sloppy as a result. Super tedious. Oops. So that structure is similarly stable. Both structures have complete noble gas configurations for all the atoms. The only difference is, to make one into the other, I have to disconnect this hydrogen, or disconnect this NH2 group, put it over here, and disconnect this hydrogen and put it over there, and then I would have the other structure. So isomers can be converted into one another, but only when covalent bonds are broken and reformed in different positions. So for this 2 down here, where I put the hydrogens in, I'm going to put enough on each atom to complete the noble gas configuration. Makes sense that I would start with the carbons, since the carbons need 4 bonds to be balanced in formal charge, and then any remaining hydrogens. And when I count up my lone pair, count up my total number of valence electrons, I have to put a lone pair in somewhere, so I put it there to complete the noble gas configuration for the nitrogen. And then the same thing here, I've got 9 hydrogens, So that's just enough to put 3 on each of these carbons and complete the noble gas configuration for each carbon, each hydrogen, and the nitrogen, and avoid any formal charge. So there are 4 ways that these could be connected. They're all slightly different in the ways, slightly different in the connections, but they're all similarly stable, so we would consider them to be constitutional isomers. So the second question here, we're looking for a constitutional isomer of cyclopropane. So typically, to make a constitutional isomer, you might say, well, let me disconnect one of these bonds and try connecting things differently. So if I've got a ring or a cyclic structure, typically one way to think about an isomer would be to, instead of connecting them all in a ring, just connect them in a straight chain. And then if I've got hydrogens to put in there, I could put them in a couple different ways. I could think about putting 2 on each, since I still have 6 hydrogens, right? To make a constitutional isomer, I can't change the number of any of the atoms. I still have to have 3 carbons and 6 hydrogens. How does that look? Is that a reasonable constitutional isomer for cyclopropane? Well, it doesn't look very good, because this carbon here and this carbon here both don't have noble gas configurations. That means they're going to be pretty unstable, so it's not very reasonable yet. If I count up the total number of electrons, valence electrons, I've got 2, 4, 6, 8, 10, 12, 14, 16, 18. So a lot of students forget to think about the electrons. If I'm drawing a constitutional isomer, it has to have all the same particles. It can't have a different number of electrons. So if I'm thinking this is a constitutional isomer, it's not yet, because I've only got 2, 4, 6, 8, 10, 12, 14, 16 electrons. I need 18. So if I want to put 2 more electrons in, now I could think about this as a constitutional isomer, but it's not very stable. It's got a negative formal charge on this carbon, a positive one on this carbon. This carbon doesn't have a noble gas configuration, so it's not very stable yet. It's not really a significant example of a constitutional isomer because it's so unstable. So I need to still rearrange a little bit more. So what I'm going to do is distribute these hydrogens differently. Sometimes you get into a mindset where you put the hydrogens on, you don't think about rearranging them, you can get stuck. So you got to rearrange the hydrogens in this case. So if I take one of these hydrogens and put it over here, so this carbon can have 4 bonds, it won't have a charge anymore. And now this carbon only has 3 bonds, so it needs more electrons. And now I can take this lone pair and avoid the charge there and then share them in there. So a molecule that has a double bond here between 2 carbons can have 3 carbons and 6 hydrogens. 3 carbons and 6 hydrogens and be a constitutional isomer of cyclopropane. Any questions about those? Alright, so let's get into some of the day 2 content then. And again, please stop me if you have questions, or message a question on the text chat if you have one. So last time we were talking about molecular orbitals a little bit, but it turns out when we're talking about molecular orbitals, if we think about carbon in the simplest organic compound you could imagine, where it's just bonded to 4 hydrogens, and the geometry that's created, we know carbon is tetrahedral, and there are lots of experiments that verify that. We know the angles. We know the 4 hydrogens are all bonded, pointing out as far apart from one another in space as possible. But if we imagine trying to form that molecule from a standard carbon atom with its normal orbital diagram, well, the carbon atom only has 2 orbitals with 1 electron with which the hydrogen can overlap, right? So we talked about this last time. We said if an atom like a carbon wants to form a covalent bond by overlapping an orbital with another atom like a hydrogen, we'll get a bonding molecular orbital, we'll get an anti-bonding molecular orbital, and to make it stable, we can only have a total of 2 electrons. If we have more than 2, then some will go in the anti-bonding orbital and it won't be stable. So that's why we're usually looking for one atom to bring 1 electron in and the other atom to bring one electron in. So typically when these orbitals overlap, we want there to be one electron in each so that there will be two total and both can go in the bonding molecular orbital and be stabilized. So this particular arrangement for carbon is not going to work to make CH4 because the carbon only has two orbitals with one electron, and hydrogen can come in and overlap with both of those, but that would only make two bonds. It wouldn't make four bonds. So we need to think about what we can do with a carbon atom to allow for four bonds to form. And so the first thing you might think of is, well, what if we move one of these electrons from the 2s up to the 2p? Now we've got four orbitals in the carbon. Each orbital has one electron, so hydrogen can bring its 1s orbital with one electron and overlap with all four of those and make the four bonds that we're trying to make. The problem with this is the geometry doesn't match up. Right? So if I think about a carbon atom with one electron in the 2s is relatively spherical and compact, and the hydrogen would get real close in there and overlap, and there'd be one electron from the carbon and one from the hydrogen, and they'd be able to form a covalent bond. That seems reasonable, but when we look at the p orbitals, the three p orbitals that exist, and the type of overlap that would occur there, I'd have to bring a hydrogen 1s in with two electrons there, another hydrogen here with two electrons here. The angles between the p orbitals are 90 degrees. And this one hydrogen would be much closer to the carbon. The one that's overlapping with the 2s would be much closer to the carbon than the others overlapping with the 2p. And that would create a situation where one of the CH bonds were more stable than the other three. That's just not the case. We know that can't be correct because that's not how CH4 exists. Right? So if we were to excite an electron up, it would at least allow us to create four bonds, but it wouldn't be the four bonds we know CH4 has with the geometry we know it would normally have. We would create 90-degree angles here between the p orbitals and the CH bonds that involved overlap there. So what we really need to make CH4 is for carbon to have four orbitals pointing out in space at 109-degree angles for the hydrogens to overlap, where there's one electron brought in from the hydrogen and one already existing from the carbon. So to do that, if we want four equivalent orbitals, and really we don't have four equivalent, we have three equivalent and then one that's more stabilizing, what we have to think about happening is we're going to mix all four of those together and create totally new orbitals. So when this happens, so-called hybridization of the carbon atom, we go from the normal 2s and 2p's that we would normally think of existing from general chemistry, and they don't exist anymore. They're wiped out from existence, and they get formed into new sp3 orbitals. And these orbitals still hold the four electrons that were there. The energy or stability of these orbitals is intermediate. It's between the higher energy, less stable p orbitals and the lower energy, more stable s orbitals. And the shapes of these orbitals are also a mixture of both p and s character. And so we call them sp3 because we mixed in one s orbital, producing that s, and we mixed in three p orbitals, giving us the p3. So 1s mixed with 3 p's, starting with four orbitals, creating four orbitals. It gives me four equivalent orbitals, which is exactly what I need to make methane and other organic compounds. So if we look at the shape of an sp3 orbital, it kind of looks like a p orbital. If I were to draw a p orbital next to it, it would be more elongated, and it would have two equally sized lobes. I didn't really draw them equal. It's a pretty terrible drawing. Hopefully you get the point there. The p orbitals are more elongated. They extend out from the carbon atom a little bit further than sp3. That's why if electrons go in the sp3, on average they're a little closer to the nucleus. It's more stable than a p orbital. If I were to look at an s orbital, the 2s, that would be more compact. It would have a node here. So by mixing the 2s with the 3 2p's, I get something that has a shape that's kind of closer to the p than the s because I mixed in 3 p's and only one s, but it's still a little bit more compact than a normal p orbital, and it has this unevenly sized nodes where there's more electron density on one side than the other. This is actually really convenient. It's a good thing that this happens because it allows for this carbon to put most of its electron density on one side, and then another carbon that's also sp3 hybridized can overlap a lot of space where of its larger lobe with this carbon's larger lobe. The more I get overlap between those atoms, the more constructive interference there is in the bonding molecular orbital, the more stable that bond will be. So what happens here is, for a single carbon atom, I'm mixing together 4 of its orbitals that no longer exist and are now converted into 4 new equally shaped and sized orbitals, and that creates something like this. So here, let me get a different color since this is all in red. Oh wait, how do I do that? Oops. Oops. Enter option. Ink color. Okay. So just to point out on this slide here, we said that there's 2 separate lobes on an sp3 orbital, and that's again because there's a planar node. So any sp3 orbital has 1 node and an sp3 orbital splitting the 2 lobes of electron density from one another. So typically though, since this lobe is significantly smaller than the other one, it's usually not shown. So in this slide here, we're not seeing the smaller lobe, right? So this is the bigger part of one sp3. Here would be like the smaller part of it. This is the bigger part of one. On the other side, there'd be smaller part would be there. So each one of these 4 bigger lobes has a smaller lobe on the other side, but those are usually not shown because they don't get involved in any orbital overlap or bonding and aren't really significant to the discussion moving forward. So the larger part of those lobes is set up to overlap with the hydrogen, and when the hydrogen comes in there, since there's 1 orbital starting off in the 1 electron starting off in the sp3 orbital and 1 electron starting off in the hydrogen's 1s orbital, when they overlap, I get the exact number of electrons I need to put all the electrons in stabilized bonding molecular orbitals that now exist over the whole molecule and allow the electrons to attract effectively to multiple nuclei at the same time. And that creates the correct angles for the CH4 molecule that we know exist. It creates equivalent bonds, so every CH4 bond is equivalent to the others because we have 4 equivalent sp3 orbitals doing the overlap with the hydrogen atoms. So what if we had C2H6? Well, that would also be sp3 hybridized. So in a C2H6 molecule, I'd have a carbon. It would be sp3 hybridized, so it would have 4 sp3 orbitals. Each one would have a smaller lobe on the other side. We're just going to exclude that from the picture because it makes it look a little too cluttered. The angles between these sp3 orbitals that are set up for overlap are going to be 109. So I'm not going to put the next one 90 degrees. I'm going to offset it a little bit at an angle. And then I would have 4 of those. And I'll try to make them all the same size and shape, although that's difficult. So if I have C2H6, then there's another carbon. Right? If I draw the Lewis structure, there's a carbon-carbon bond there. And there are 3 hydrogens on each carbon. This is called ethane. And in this structure, to make a carbon-carbon bond, there's going to be overlap head-on between the 2 carbon atoms' sp3 orbitals. And the other remaining sp3 orbitals will be overlapping with the 1s of a hydrogen. And that overlap will create the CH bonds at the correct roughly 109 degree angles. And then there'd be 2 electrons in each area of overlap. So all the electrons would go in bonding molecular orbitals and it would be especially stable. Let's take a look at that type of situation for water. Right, we know water has 2 lone pairs and 2 bonds. Does water have to hybridize? Yes, it does, because if it didn't hybridize, then the oxygen, like we showed on the previous slide, the oxygen would have, that oxygen atom would have a 2s. Maybe a lone pair would sit in that 2s. then I have a p orbital, maybe that holds a lone pair, and then another p orbital to overlap with the hydrogen. That's going to create a 90-degree angle because p orbitals are at 90-degree angles to one another. But we know the angles in water are not 90 degrees. So similar to how the carbon forms an sp3 hybridization to form 4 separate sp3 orbitals for 4 separate areas of overlap, water would do the same thing. It will also be sp3. And if we look at the picture of that, the carbon that's sp3 is going to be very similar to the oxygen. The oxygen is going to have one sp3 orbital that holds a single electron for overlapping with the hydrogens, 1s. That will bring in another electron. And then it's going to have another sp3 orbital at an angle not 90 degrees, more closer to 109. Actually, in this case, it's closer to 105. And that would be another electron overlapping with the 1s of the hydrogen, bringing in an electron. So my 2 bonds would exist in that way. And then the other 2 sp3 orbitals, would contain lone pairs. So typically a lone pair on an atom in a molecule exists in a hybridized orbital. It should pretty much always be, not always, but most of the time it's going to be in an sp3 type orbital. It could be sp2 or sp, and we'll talk about those here in a couple minutes. So what if I have a double bond? Well, that creates a situation where the hybridization is different, because here I only need 1, 2, 3 orbitals to overlap head-on with the atoms that are making bonds. If I'm only making bonds with 3 atoms, then I only need 3 orbitals to provide the overlap between those atoms. So in this situation, I would form what's called an sp2 hybridized orbital. By mixing in 2 of the p's with the s instead of all 3, I get slightly more stable orbitals than they were when they were sp3, because now it's a 33% s character, whereas before it was only 25% s character out of the orbitals that are mixed in there. A bigger proportion of that now is s versus what it was in the sp3 orbitals. So these orbitals are pretty stable. They each hold an electron. And then if I looked at that carbon atom and where the electrons are, again, the sp2 orbitals are at 120 degree angles. They're all in the same plane as one another. So when the hydrogen comes in to overlap with its electron here and here, and the other carbon that's forming the double bond brings in its orbital with its electron there, I can make all 3 bonds in the same plane. And we know that that ethylene molecule here has roughly 120 degree angles, and it's flat. That's why it's drawn on this little flat thing here, because it's a flat structure. All the atoms are in the same plane. If you look back at the shape of an sp3 hybridized carbon, it's not flat. The 4 bonds are all pointing out in different directions 3-dimensionally. So we know if a structure is flat, it can't be an sp3 hybridized atom. In this particular case, it's going to be sp2 because we're mixing in only 2 of the p's with the s to make 3 sp2 orbitals. And we're leaving this 3rd p orbital untouched or unhybridized. It still exists, right? That's here. So sometimes students get confused and feel like the blue is a different orbital from the red. That's not true. The red and the blue here are both part of the unhybridized p orbital, right? We know a p orbital has a node, and there's 2 lobes for every p orbital. So that's why there's 2 lobes here shown, because they're equal in size above and below the plane of the carbon. And that's going to hold an electron, and that's going to allow for the double bond to form. So we'll see that here as we go through in a minute. So as we showed, if I'm forming a carbon-carbon double bond, part of that is a sigma bond. The sigma implies that we're talking about head-on orbital overlap. So this carbon's orbital is overlapping head-on with the other carbon's orbital. They're heading, they're kind of elongated. this elongated structure is overlapping as much as possible head on right toward the other carbon's sp2 orbital to make that bonding molecular orbital that would hold 2 electrons and stabilize them really nicely. These are also sigma bonds. Hydrogen can really only ever be involved in a sigma bond because its 1s is spherical. It doesn't have like any directionality. When it comes in and overlaps with the carbon's sp2, that's also going to be considered head-on, or in addition, it's going to be considered a sigma bond. So each of these carbons is going to make a nice CH sigma bond, another CH sigma bond, and a CC sigma bond. But then what you may be noticing is this p orbital here has an electron, and so does this one. So if these carbons can get close enough for these orbitals to start overlapping side by side, that is going to create a molecular orbital as well. Anytime two atomic orbitals overlap, I get both constructive and destructive interference, and I form molecular orbitals. So that's what we see in a pi bond. A pi bond is a different type of bond. It doesn't involve head-on overlap, it involves side-by-side overlap. And so anytime I've got a double or triple bond, only one of the pairs of electrons shared between those two atoms can be a sigma bond, and the sigma bond is right in the plane between the atoms due to the head-on overlap. The electrons exist mainly in the area of overlap in the constructive interference bonding molecular orbital, attracting effectively to both carbons. That's a sigma bond. The pi bond involves overlap above and below the plane of the carbons, and so that electrons that are in the second part of that double bond, they exist in a pi bond. So any bond between two atoms can only ever involve at most one sigma bond, because the sigma bond is that head-on overlap right between the atoms. The pi bond occurs above and below the plane when the p orbitals line up and overlap side by side. So let's take a look at the molecular orbitals that result from that pi bond. I know these a little blurry. I grabbed them out of the textbook, and when I zoomed in a little bit, the resolution was lost somewhat. But if we look at this situation, we've got our two carbon atoms, one p orbital here, overlapping with the other one. So if they overlap with different wave signs, then the area of overlap cancels out. And that's why I get a node created right here. So this node here is created by the destructive interference. There's already a node here because p orbitals naturally have a planar node splitting their two lobes. But that now creates a situation where I have two nodes in a pi anti-bonding molecular orbital. So the electron density in the red and blue areas here isn't really close to the nuclei, and that's really quite unstable, which is why electrons don't go in there. When I only have two, they go in the bonding molecule. And as we said, when the electron overlap or the orbital overlap involves equal wave, the same wave sign, so if this is both positive and positive mathematical sign, and this is negative and negative mathematical sign, then they'll add together above and below the plane, and I'll increase the electron density in the area between the atoms. It's not right between the atoms because that's where the sigma bond is. It's a little above and below the plane, but they're still close enough. The electrons here and above and below the plane are still close enough to attract to both nuclei, and so it's a relatively stable situation. It's not as stable as a sigma bond because the electrons are not as close to the nuclei though. So that's my sp2 hybridization. Could sp2 hybridization be appropriate for methane to make CH4? Well, the answer is no, and we also want to understand why that is, and that's because to make CH4, I'd have to have a hydrogen come in and overlap with every one of these orbitals. And that would create a CH4, because each hydrogen would have one electron to share with the one that's already there, and that would go in the bonding molecular orbital. But that's just not how CH4 exists, right? That would create 90-degree angles between this CH bond and this CH bond, because the p orbital is at a 90-degree angle to the hybridized sp2 orbitals. So some of these CH bonds would be 120 degrees, which is the angle between sp2s, but some would be 90 degrees, and that's just not matching up with the way we know methane exists. So we know the carbon in methane, it has to be sp3 hybridized. That's the only way to create all four orbitals at the right angles for the hydrogens to come in and overlap and make methane with the correct geometry. Question?
Yeah, I have a question on the previous slide for more like a clarification. So, when you drew your wave signs, the node is formed in antibonding when the same wave signs come together?
No, so I was speaking pretty fast here. This situation where they have the same wave sign, it creates the bonding molecule. So there's already a node there, but there's no additional node because when they have the same wave sign, they constructively interfere. So if I had the two carbons overlapping their p orbitals side by side, and this one was plus minus and this one was minus plus, then they would cancel out in the area of overlap. That would create the extra node that's shown here vertically, where the areas of overlap would be canceled.
Gotcha, that makes sense.
Awesome. Thank you for clarifying that. And any other questions so far? All right, so that allows us now to have the background to answer the remaining quiz questions. Well, not all of them, but some of them. So most of you answered these correctly in your Google Docs, so that's always good. The 3S, we actually talked about that last time. So we know an S subshell is spherical. The third energy level is kind of far out from the nucleus, so that's going to be a relatively large sphere if this is my nucleus. Most of the electron density is somewhere around there, but we know that there are two nodes. If it's an atomic orbital, then the number of nodes is always equal to n minus 1. And so if n is 3, because we're in the third energy level, 3 minus 1 equals 2. And if it's an S, everything is spherical. So in the 3S, there's some electron density relatively close to the nucleus. Then there's a node. Then there's more electron density outside of that. Then there's another node. And then the remaining electron density is outside of that. And if this were to overlap with another atom, it would be the outer area of that overlapping to create molecular orbitals. So what about a sigma antibonding molecular orbital? Well, I realized when I started looking at your quiz questions that this question was a little unclear as to exactly what it was asking. Probably should have clarified here whether what type of sigma bond we're talking about. So there's two possible ways to think about this. If it's like a sigma bond between two hydrogens, or a sigma bond between a carbon and a hydrogen, or between two carbons, the answer could be a different answer. So we know if it's antibonding, specifically we're talking about the destructive interference. Right? So if there were two hydrogens overlapping their 1s, destructive interference would result in a new node forming there. And so the electron density of those hydrogens would be on either side of that node. So I would have one node if it were a hydrogen covalent bonding to another hydrogen, forming a sigma antibond, antibonding molecular orbital. For the carbon, now that we've talked about hybridized orbitals, if we assume maybe this carbon is sp3, it would have already a larger lobe and a smaller lobe, right? We saw the shape of the sp3. There's already a node there, and the hydrogen would overlap there. And if it's destructive interference to create an antibond in that area of overlap, that would cancel out, so I would get a second node. So there'd be some electron density around the carbon. There's already a node here. A new node would be created due to the destructive interference in the area of overlap, and then there'd be more electron density around the hydrogen. So there'd be two nodes if it were a CH bond. And in the CC bonds we already looked at today, normally we don't always think about all the nodes, because typically when we think about an sp3 hybridized carbon, we only think about the larger lobe of electron density. The smaller one is often ignored. But there are two there, and there is already a node there. So if two carbons that both were sp3 overlap their orbitals, there are already two nodes. And if the area of overlap results in destructive interference, that would create a third node. So there'd be 3 nodes if it were a CC sigma bond. Sometimes these 2 nodes on either side aren't really considered important though, because they were already there to begin with. It's the formation of a new node in the area of overlap, if it's an anti-bonding molecular orbital, that makes that especially unstable. In an sp3 orbital, we know that carbon, a single sp3 orbital, so we know there's always going to be 4 of them if it forms sp3 hybridization, but a single sp3 orbital has 2 lobes that are lopsided in electron density and 1 node. And now we just looked at the pi bonding and anti-bonding, so it's probably easier to just go back and visualize that here. The pi anti-bonding has 2 nodes, 1 node that was already there, and then the new node that's created when the destructive interference occurs. So that's 2 total nodes. In the pi bonding molecular orbital, there's already a node there to begin with between the carbons, and if they overlap with the same wave sign, they don't cancel, so I don't create a second node. There would only be 1 node in that molecular orbital. So hopefully that clarifies any questions you may have had on the quiz. When I check out your answers, if they're not correct, I'll give you some individualized feedback about what you may have answered there. So the other situation we haven't talked about yet is when your carbon is sp hybridized. So here, the way this shape is shown here is not really correct, so let me try to clarify this. The book didn't really do a very good job of this one detail. Here we're just mixing one of the p orbitals with the s to create sp, right? So sp means it's 50% s, 50% p. The shape of this orbital is similar to sp2 and sp3, but it's more compact, right? Because now half of the characteristics of this orbital come from the 2s that's mixed in, and the other half come from the 2p that's mixed in. And so if it's 50-50 s and p versus sp2 and sp3, which have more p character than s, the 50-50 mixture here creates a relatively compact orbital. But here we're leaving 2 p orbitals unhybridized. And so if you look at a carbon that has this hybridization, each carbon that has this hybridization creates an sp orbital on one side and another sp orbital on the other side. The sp orbitals are always 180 degrees apart from one another. So if we're looking at this carbon and it's sp hybridized because it's part of a triple bond, I can form one sigma bond when both carbons' sp orbitals overlap with one another and create constructive and destructive interference. The 2 total electrons will go in the bonding molecular orbital rather than the anti-bonding one. I can also create a sigma bond where the hydrogen overlaps with an sp orbital. That's a head-on overlap as well, so that's another sigma bond. But between 2 atoms, there can only ever be a maximum of 1 sigma bond. So when this carbon's sp overlaps with the other and the electrons go into a molecular orbital, resulting from constructive interference or the bonding molecular orbital to be stabilized around both carbon atoms, they're mostly occupying this space of overlap, attracting effectively to both atoms. But they're already occupying this space. So in a double or triple bond, I can only have 1 pair of electrons in the sigma bond or in the space right between the nuclei. So similar to the double bond here, we keep the unhybridized p orbitals and we imagine those overlapping side by side to make a pi bond. So you can have up to 2 pi bonds between carbons, but only ever 1 sigma bond. And so if we're looking at this 3-dimensionally, this p orbital here, pointing straight up and straight down, that's one orbital. That p orbital, maybe that's on the y-axis, pointing straight up and down. The neighboring carbon also has a p orbital on the same axis. So that's going to overlap both above and below the plane And it's going to create a pi bonding molecule and antibonding, but since there's only 2 total electrons, they'll both go in the bonding molecule orbital and exist not right between the nuclei, because that's where the sigma bond is, but the pi electrons exist a little bit above and below the plane of the nuclei, still close enough to attract to both nuclei though. So that's one pi bond. And so a lot of times that gets confusing for students. When you see the overlap occurring above and below the plane, that's not 2 bonds. Each p orbital has 2 equally sized lobes, so when they both overlap, it's still only 1 bond because there's still only 2 orbitals overlapping there. So to make the other pi bond, to make it a triple bond instead of just a double bond, there's another unhybridized p orbital. And this one might be in the z-axis pointing away from you and then out at you. And if the other carbon has the same thing, then those can overlap red on red and blue on blue to make the other constructive interference in the other bonding molecule that the other 2 electrons will exist in. And so this is more of a 3-dimensional situation. It's not easy to explain it and visualize in a 2-dimensional piece of paper or screen, but these p orbitals are perpendicular to one another and they have to overlap side by side to make the pi bonds. So the geometry of this molecule is linear, or at least the 2 carbons' geometries are linear, because I could draw a straight line between the atoms, the carbon and hydrogen atoms, but the p orbitals are not on that line. They're kind of sticking out into space. So the electron cloud isn't necessarily all on the same line that the nuclei are on. I just wanted to point that out. Any questions about triple bonds or double bonds?
Do triple bonds form like a steric number of 2?
Yeah, we're going to talk about steric number. Yeah, triple bond. So if I have an atom involved in a triple bond with some other element or the same element, the steric number is the total number of sigma bonds and lone pairs. So if there's another sigma bond here, or if there's a lone pair there, which is what it would need to make its noble gas configuration and get 8 total valence electrons, yes, the steric number would be 2, because if I do have a triple bond, 2 of the 3 parts of that triple bond are always going to be pi bonds, and they don't count toward counting up the steric number. So if I don't count the pi bonds, which I shouldn't when I'm counting the steric number, I've got 1 pair of electrons here and 1 pair here, or 1 pair here and 1 pair there. So in both instances, the steric number is 2. Very good, Ethan. Alright, so let's answer these questions, make sure we understand a little bit more detail about these types of bonds. So which should be stronger, a pi bond or a sigma bond? Well, if I'm looking at a carbon-carbon sigma bond, that results from head-on overlap. If I'm looking at a carbon-carbon pi bond, that results from the p orbitals overlapping side by side. So what's the difference? Well, over here, I have a lot more overlap. These ones only kind of overlapped a little bit on the edges. So that's one factor that affects this. The more overlap there is, then when the bonding molecule is created by the constructive interference, the more chance there is that the electron density will increase in the area between the nuclei. So this one is stronger. The sigma bond is stronger because there's more effective overlap. That's one reason. What's another reason that the sigma bond is stronger? Well, look at where the electron density is. In the sigma bond, due to the fact that they're head-on overlapping right between the nuclei, the electron density is much closer to the nuclei, versus here, the electron density is mostly above and below the plane of the nuclei, so it's not as close. So the electron density is closer to the nuclei. That's a big factor there as well. So what that means is, if I'm looking at a carbon-carbon double bond, now we can actually start to think about reactions that these molecules might undergo. if I have a reaction where I've got a pi bond, because anytime atoms are sharing electrons, only one of the bonds between them can be a sigma bond. That would be the more stable one. The other one would be the pi bond. If I react this with hydrogen, that chemical reaction should be exothermic, because by breaking this bond, which is a sigma bond, and breaking a pi bond, which isn't very stable, so it shouldn't take that much energy, I don't have to put that much energy in to break these two bonds. Once they're broken, and then the hydrogens bond to the carbon, now I've got a molecule that only has sigma bonds. So I broke two bonds, and I formed two bonds. Maybe this one and this one are the new ones. Breaking two bonds, forming two bonds, you might say, well, I don't know if that's going to release energy or absorb energy. It depends on whether the bonds that are breaking require more energy to be absorbed to break them, or whether the bonds that are forming release more energy when they're formed. And so here we can actually make a judgment and say, well, since one of these bonds breaking was a pi bond, it shouldn't take that much energy, and so that means the amount of energy I have to put in, potential energy I have to put in during the reaction to make the reactants break their initial bonds isn't that much. But when the new bonds form, more energy is coming out, and so delta H should be negative because more energy. These are more stable bonds and lower in potential energy than the initial pi bond, which is higher in potential energy. And that's a theme that will come back a lot throughout OChem 1 and 2, where we're comparing sigma bonds and pi bonds and understanding that sigma bonds are more stable for these reasons. What about a sigma bond between two sp3 hybridized carbons versus a sigma bond between two sp hybridized carbons? Get rid of this stuff here so we can talk about that. To understand this second question here and answer it completely, we really have to understand the difference between the Sp3 shape versus the Sp shape. Right? So what we said was, if we were to draw an Sp3 right next to an Sp, what would the difference be in their shape? Well, they're both a mixture of S and P. The difference is the Sp is 50% S, 50% P. So it's a 50-50 mixture because there's equal amounts, one S and one P mixed together. Here I'm mixing all three P orbitals with one S. So it's only 25% S and 75% P. So these are more like P orbitals, and these are more like a 50-50 mixture. The S orbital, the 2s, is more compact than the 2p. So when you think about the 2s, it's going to be more compact. The electron density is going to be closer to the nucleus. And so if I'm mixing that in a 50-50 ratio, if I look at the shape and size of an sp orbital, it's more compact and more spherical because there's more s character. Versus an sp3, it's more elongated. This is a bit of an exaggeration, but I'm trying to make a specific point here. It's more elongated, so the electron density is not as close to the nucleus. So if I'm going to make two sp3 carbons form a sigma bond, they can only get so close, and their orbitals will, these long elongated sp3 orbitals will overlap, versus a sigma bond between two sp hybridized carbons, where the orbitals are more compact, the carbons will get closer. So the longer the orbital, the less there is of a need for them to get close to one another to overlap the majority of, or the effective overlap between the orbitals. So the sp3 is longer than the sp sigma bond due to the shapes of the orbitals, which result from the quantity of s, or the ratio of s and p that are mixed together in the hybrid orbitals. So hopefully that makes sense to you all. So we can see the difference in the bond lengths here. Any questions? We can see the bond length differences here. So this these differences are in part what we just said, but they're also affected by the pi bonds as well. So in the case of an sp3 overlap, there's no way to form a pi bond because all three p orbitals are already mixed in to make these sp3s. In the case of an sp, there's still unhybridized p orbitals here and here, and I didn't draw close enough to see them overlapping, but if they're overlapping side by side, that's more electron density above and below the plane of the carbons, and that pulls, that attraction between the electrons here and the nuclei of the carbons kind of pulls them a little bit closer as well. So the double and triple bonds are also shorter because the pi bonds help attract the carbons closer together, and since there are no pi bonds in an sp3 hybridized carbon, they're definitely not going to be as close. The bonds are not going to be as short. And so we can see that here. Again, in angstroms, 1 10 to the minus 10th this length of a meter. So these are obviously very short, but they get shorter and shorter the more electrons you put between them. And they're also shorter because it's an sp overlap versus the more elongated sp3 overlap. Alright, so if we want to talk about molecular geometry so that we can show the shapes of these molecules properly and analyze their polarities properly, so we can then eventually look at their properties and reactivities, steric number is actually a really useful way of helping you determine the geometry for an atom correctly. So steric number is probably a new concept to you, but it's pretty straightforward. The steric number is the sum of the sigma bonds, not any pi bonds, they don't count, just the sigma bonds plus the number of lone pairs. Right? So in the case of this carbon, we're just looking at this carbon so we can analyze its geometry and what shape it has. It's got 4 sigma bonds and 0 lone pairs. So 4 plus 0 gives it a steric number of 4. In the case of the nitrogen, it has 3 sigma bonds and 1 lone pair. So 3 plus 1 is also 4. And here for water, the oxygen has 2 sigma bonds and 2 lone pairs. And so adding 2 plus 2 also gives me 4. So these all have the same steric number. What does that mean? Well, the steric number is especially relevant in determining the type of hybridization necessary for the central atom. So when the steric number is 4, there will be some exceptions to this we'll talk about later, but for now you don't have to worry about them. Whenever the steric number is 4, it should be most of the time sp3 hybridized. And what does that mean? Well, we talked about sp3 and we said when something's sp3 hybridized, the atom has this specific shape. The orbitals extend into space at 109-degree angles and allow for sigma bonds to form through head-on overlap with other atoms. So if it's got a steric number of 4, that's because it needs to create 4 sp3 orbitals to point into space to hold the sigma bonds and or lone pairs. So whether it's 4 sigma bonds like here, or maybe 1 sigma bond and 3 lone pairs, I still need 4 orbitals if the steric number is 4, and so that requires it to be sp3 hybridized. So there are some exceptions to that. We'll talk about them a little later when we see how they're relevant. So when the steric number is 4, we know it's going to be sp3. If the steric number is 3, it should be sp2, because that means that the atom needs to hold 3 sigma bonds, or 2 sigma bonds and a lone pair, or 1 sigma bond and 2 lone pairs. Some combination of sigma bonds and lone pairs adding up to 3 requires it to be sp2, because sp2 creates 3 orbitals to hold those sigma bonds and lone pairs. And if the steric number is 2, then I only need 2 sp orbitals to hold the sigma bond and lone pair electrons. So you should hopefully see the relationship between the steric number, which hopefully you can calculate if you can determine how many sigma bonds and lone pairs an atom has, and the type of hybridization that the atom has. Because it is common for students to have trouble recognizing the type of hybridization. So my recommendation is calculate the steric number first, and then relate that to the type of hybridization that the atom has. So here are the three compounds we just talked about that have a steric number of 4. The methane, the ammonia, and the water all have steric number of 4 because they all have a combination of sigma bonds and lone pairs that add up to 4. And notice that their shapes are very similar. So if I take this general tetrahedral shape for methane, where it's got 4 sigma bonds, and then maybe just take this bond off and replace it with a lone pair, well then I create something that's almost the same exact shape, but now I just have a lone pair occupying that space instead of a bonded pair. If I do that again and remove another bond and put a lone pair there, then I have something that's almost the exact same shape as water. So these 3 molecules have different geometry labels, but their shapes overall are very similar because they're all sp3 hybridized and they all involve 4 sp3 orbitals pointing out into space at roughly 105 to 110 degree angles. The name for this shape here is tetrahedral. Tetra is a prefix that means 4, and that's because there are 4 atoms attached to the central atom. That's pretty easy to recognize. Anytime a central atom has 4 other atoms attached to it, pretty much always going to be tetrahedral. The shape of this is called trigonal because the atom has 3 other atoms attached to it. So in our geometry labels, the lone pair is relevant to where the atoms will be pushed in space and where they'll be pointing out in 3 dimensions. But when we actually get the name, it really depends on where the nuclei are. So there are 3 nuclei attached to my central atom, so this is trigonal, and because of the shape and the angles here, the hydrogens are not in the same plane as the nitrogen. In fact, they're more like forming the base of a pyramid, where the nitrogen is at the top of that pyramid, so we call it trigonal pyramidal. And then anytime you have a central atom with only 2 atoms attached, it's either bent or linear. And in this case, it has to be bent because we know the angle is not 180. If the atom's sp3 hybridized, the angle is going to be around somewhere close to 105 to 110. And so there's no way for that to be linear, so that one would be bent. So let's look at some more examples that relate to that general idea with different hybridizations. So here we've got BF3. And you really have to start by drawing a Lewis structure here to calculate the steric number, right? Because we said the steric number depends on how many sigma bonds and how many lone pairs the central atom has. And if you don't correctly draw the Lewis structure, you probably won't correctly know how many sigma bonds and lone pairs it has. So you really have to build everything in this class on the foundation of drawing Lewis structures. And if you've struggled with that, you should practice that and get my feedback on your work so you can get up to par on that moving forward. But for BF3, boron is in column 3A, fluorine is in column 7A, so that's 24 total electrons. And when I put the boron in the center and the fluorines on there, with those 24 electrons, I have just enough to complete the noble gas configurations for the fluorine, but not for the boron. So you might say, well, why not put one of the fluorine's lone pairs in to make a double bond? That way, the fluorine here will still have a noble gas configuration, but then the boron will as well. Is there a reason why that's not ideal for BF3? Normally the noble gas configuration is our top priority. In this case though, it's a situation where we're not likely to see this double bond here, even though it gives the boron 8 electrons to make its noble gas configuration, and the fluorine still has 8 to make its noble gas configuration. This would create some really unstable formal charges. So not all formal charges are equally unstable. If I calculate the formal charge for the boron here and the fluorine here, these are really bad. So we were saying last time how when I calculate a formal charge on a small atom, it creates a ratio of positive to negative that's not close to 1, or it's not balanced, and it's really unstable. So boron normally has 5 protons. Putting an extra electron around it gives it 6 electrons. So 6 to 5 ratio, not very close to 1, not very stable. The smaller the atom, the more extreme the ratio is when there's an extra proton or electron. In the case of fluorine, we have an even worse situation. Fluorine is the most electronegative atom that exists. It has very little shielding to repel any electrons from the 9 protons in its nucleus, and with 9 protons in the nucleus, it's actually really nicely, it will really nicely attract shared electrons. So these electron pairs, in addition to the fact that the boron is negative, and that negative will repel the shared electrons, the fluorine naturally already attracts them well, and when the fluorine's positive, the positive charge helps it to attract electrons even more. And so this is a situation where the molecule just happens to be more stable without a noble gas configuration around the central atom, because it avoids these really unstable formal charges. And if you do imagine the formal charges forming, you can easily see how this electron pair is just going to move back out here to the fluorine to balance its charge, because if it's shared there, it's just really too strongly pulled by the fluorine to remain shared effectively. Either way, though, whether I imagine it with 3 single bonds or 2 single bonds and a double, the steric number is still calculated the same, because as we just showed a minute ago, if I do have a double bond, only one of the bonds can be a sigma bond, and the rest has to be pi. So I still only have 1, 2, 3 sigma bonds. Whether I imagine this is the correct structure or not, if I imagine this one, it's still 3 sigma bonds. So 3 sigma bonds and no lone pairs gives me a steric number of 3. And when I have a steric number of 3, I know that it's going to be sp2 hybridized. And so what are the 3-dimensional shapes of sp2 hybridized atoms? They're planar. The 3 sp2 orbitals that are here on the bond overlap with the fluorine are all in the same plane. You can imagine those flat in the plane of the screen. If that were true, there'd still be an unhybridized p orbital. I only mixed in 2 out of 3 p orbitals from the second energy level into making these sp2 orbitals. So the remaining p orbital will be behind here and coming out at you if the boron's sp2 orbitals are in the plane of the screen. This will be pointing straight back and straight out at you. But that's empty. There's no electrons in there. So that's the shape of this sp2 hybridized atom. So sp2 atoms are always flat. And if the central atom is bonded to 3 other atoms, as we just showed on the previous slide, that's called trigonal, because there's 3 atoms attached to the central atom. And since it's flat, we call it trigonal planar. It's all the nuclei are in the same plane, and that's what makes it trigonal planar. How many electrons are aboard on its hybridized p orbital? We already said that. That's 0. So that p orbital that sticks out behind and in front of the plane of the molecule has no electrons in it. And the answer here is yes. Vesper theory, if you recall from Gen Chem, basically is just confirming what the molecular orbitals show, which is that the bonds or pairs of electrons around the atom will want to spread out from one another as much as possible. And if I've got 3 groups of electrons to spread out, the greatest distance I can create between them is 120 degree angles, putting them all in the same plane. And so that's the same geometry I would analyze using Vesper theory. I'm also getting through the molecular orbital theory, or through the hybridization of the sp2 orbitals that are created here, and the geometry I expect for those orbitals in space. This molecule isn't finished. So let's say I've got a carbon here and a carbon here. So what's the molecular geometry of the nitrogen? Well, let's start by calculating the steric number. So we'll do the nitrogen here. The steric number is equal to the number of sigma bonds plus the number of lone pairs. So I'm going to add sigma bonds plus lone pairs. So for the nitrogen, I've got 1, 2 sigma bonds. I can't have 2 sigma bonds between the same 2 atoms. So anytime 2 atoms share electrons, only one of the shared pairs can be a sigma bond. So I've got 2 sigma bonds total, and obviously 1 lone pair. So the steric number is 3, and when the steric number is 3, it's sp2 hybridized, right? The total number of s's and p's mixed in should equal the steric number. And so that means if I were to look at the shape of this nitrogen, if it's sp2, then there's 3 sp2 orbitals kind of sticking out in space at roughly 120 degree angles. One would hold a lone pair, and one would involve head-on overlap with this carbon. The other would involve head-on overlap with the other carbon. And so the electron group geometry would be planar. But if we're looking to label the molecular geometry, if the central atom only has 2 other atoms attached to it, it's either linear or bent. And so the existence of this lone pair prevents it from being linear. The fact that it's sp2 means that the angles between all of the sp2 orbitals are roughly about 120, and so it's definitely not linear because that would require angles of 180. What's the steric number and geometry of this carbon? Well, 4 sigma bonds and 0 lone pairs, and so that's tetrahedral. It has 4 atoms attached to it, 3 hydrogens and a nitrogen. 4 atoms attached, all with single bonds, tetrahedral. Now what about this carbon? Here the steric number is 3. It's got 1, 2, 3 sigma bonds and 0 lone pairs. Steric number of 3 means it's sp2. This one was sp3. And here it's trigonal planar because there are 3 atoms attached to the carbon. Trigonal. 3 atoms attached to the 2 hydrogens and the nitrogen attached to the carbon. And it's planar because of the sp2 hybridization that we just saw on the last slide. So when your atoms sp2 hybridized, all of the atoms attached to it are going to be in the same plane, but then there's going to be a p orbital perpendicular to that plane. So this carbon is going to have a p orbital that overlaps with this nitrogen's unhybridized p orbital side by side. That's going to make the pi bond here, and then the carbon will have a couple sp2s to overlap with the hydrogens attached to it, given that the carbon is sp2 hybridized. All right, a couple more examples. Here we got BeH2, so beryllium. I want to start by drawing a Lewis structure. We know hydrogen can only ever have 1 bond. So looking at beryllium, it's in column 2A on the periodic table, and hydrogen's in 1A. We've got 2 of those. So I've got 4 electrons, and they're already in there. That means I can't put any lone pairs on the beryllium. It's not going to make a noble gas configuration. It doesn't have enough protons to attract in 8 electrons around it anyway. So here the steric number is 2 sigma bonds plus 0 lone pairs. 2 plus 0 is 2. And so what will the hybridization be? Well, it'll be sp. Right? For the central atom, it needs 2 orbitals to overlap with the 2 hydrogens. So it only needs to mix 1 s and 1 p to make those 2 new orbitals. There will be 2 empty p orbitals still around that. So since I'm only mixing 1 of the p's in with the s to make 2 total orbitals, it's going to be sp hybridized, and that means it's going to be linear. Right? Any sp hybridized atom should for the most part be linear, because sp hybridized means that the central atom has 2 orbitals with a 180 degree angle between them that are used to make the bonds or hold lone pairs, which there aren't in lone pairs in this case, obviously. If we look at the CO2, drawing the Lewis structure for that, I end up with double bonds there. Actually, let me scrap that and start over. So initially, I would probably start with single bonds, count the valence electrons, 4 from the carbon, 6 on each oxygen. I've got 2 of those, so that gets me to 16 total. I only need 4 to make the 2 bonds initially, so I've got 12 left. So 2, 4, 6, 8, 10, 12. I've got enough to fill the noble gas configurations for the oxygen, but not the carbon. So I've got to share in here another couple pairs to complete the noble gas configurations for all the atoms and give them all octets. When I do, what's the steric number for the carbon? 2. As we said, anytime 2 atoms have a double or triple bond, only one of those bonds can be a sigma bond. So this carbon's got 2 sigma bonds and 2 pi bonds. The steric number is just the sigma bonds plus the lone pairs, so we don't count the pi bonds. So I've got 2 sigma bonds, and then if the steric number is 2, it's going to be Sp hybridized, and it's going to be linear. Right? So if we were to look at this carbon's orbitals, what would it look like? It's hard to draw. I'll do my best. So the carbon is linear, so it's got an sp orbital here to overlap with this oxygen. So I'm not going to worry about the hybridization of oxygen at the moment, but it'll have some kind of orbital overlap with the carbon. And have another sp orbital on the other side. I'm only mixing one s and one p, so only mixing 2, I only get 2. I've got one orbital here to overlap with one atom, the other orbital to overlap with the other oxygen. So those are my 2 sigma bonds. The orbital overlap occurs right between the atoms, constructive interference, creating bonding molecular orbitals. I've got 2 electrons in each one, both going in the bonding molecular orbital, both being well stabilized. So if the carbon is sp though, and I'm only mixing in one of the p orbitals from its second energy level, I still have 2 p orbitals left. I've got one elongated p orbital, so I'm going to put plus minus to indicate that those would have opposite wave signs. These are perpendicular. The p orbitals are perpendicular to the sps, and they're perpendicular to the other p orbitals. So here I would have another p orbital here, and that would have opposite wave signs on opposite sides. Are these p orbitals empty? No. They're used to make the 2 respective pi bonds. So one of these oxygens is going to have a p orbital in the same plane as this one, and it's going to overlap both constructively and destructively, but when the constructive interference occurs here and down here, that creates one of the pi bonds on one side. The other pi bond has to occur perpendicular to that, because this carbon can only have 2 p orbitals and they're perpendicular to one another. So this oxygen would have an unhybridized p orbital, and its wave would overlap side by side here and here. So in carbon dioxide, the central carbon atom is sp hybridized. It's a linear structure, but when we look at the bonds in space, the sigma bonds are right between the carbon and the oxygen nuclei. Those are the most stable parts. The pi bonds aren't as stable, but they do create overlap both above. The pi bond has overlap above and below the plane. And then the other pi bond has also electron density above and below the plane of where the carbon-oxygen nuclei are. So here's just a slide to basically summarize everything we just talked about. So there are really only 5 total geometries that you could labels that you really need this semester. We won't really be looking at examples that go beyond these 5 labels. And so using this flow chart, if you work with it enough, hopefully it will become like natural to you to work through this, to see when structures are linear versus bent, and when trigonal structures are planar versus pyramidal. It depends on the steric number and the type of hybridization, as we just showed in those examples. Any questions about geometry? so let's talk about polarity. As we were saying last time, we talked about individual bond polarities. Anytime two atoms have some kind of electronegativity difference, that causes what we call induction. Induction is just a fancy word for electrons shifting toward one atom or the other depending on which one's more electronegative, right? So we know the more electronegative atom's going to attract electrons better, and that shifting of the electron cloud is what induction is. Right? So when carbon bonds to hydrogen, carbon's more electronegative, and so the induction causes the electron cloud to shift a little bit more toward the carbon, creating a little negative on that side. And carbon bonds to oxygen, oxygen's more electronegative, so that creates a negative on this side and a positive on that side. So these partial charges are created by the induction or the shifting of the electron cloud toward the more electronegative atom, bringing more negative charge to that side of the bond. So we talked about bond polarity. Now we want to extend that to molecular polarity, or the polarity of the whole entire structure combined. So to do that, we have to look at all the individual bond polarities and then kind of average that all out. So there is a mathematical or quantitative...
Dr. Bio?
Yes.
I have a question.
Yes.
For the exams, will we be given the values for each of the electronegativity values for each of the atoms, or will we have to memorize those like values?
So the numerical values for the electronegativities may be given, or they may not be, depending on the situation. So if you have two elements in the same row on the periodic table, I might not give you the values, because I would expect you to know that as you go from left to right on the periodic table, you're adding more protons to the nucleus, and so those elements with extra protons are going to pull the electrons more, and they're going to have a greater electronegativity than the elements to the left of them on the periodic table. Or if I give you two elements in the same column, you know, as you go down a column in the periodic table, you're adding layers of electrons every row you go down. So as I go from the top, like fluorine to chlorine to bromine to iodine, as I go down, I'm adding layers of electrons. So now there's more and more core layers of electrons between the shared electrons in the atom. And so the atom can't attract the shared electrons and will thus have a lower electronegativity as I go down toward the bottom of the periodic table. If I give you two elements, or you have to work with elements that are not in the same row and also not in the same column, like for example, comparing hydrogen with phosphorus, right? They're not anywhere near one another. I would not expect you to know which has a higher electronegativity. So on an exam in person, if you feel like there's no way for you to know which element's more electronegative, I would either give you that information on the exam, or if I forgot, I would be happy to write it on the board during the exam, because I don't expect you to memorize electronegativity values for every element, but I do expect you to understand what electronegativity is, what the factors are that affect it, and to be able to rank electronegativity for elements if they are in the same row or in the same column. Good question. All right, so I guess we'll keep going. Does anyone have any other questions? So when we're dealing with overall polarity, there is a mathematical way to calculate that, and there are specific units involved in that. For the most part, I won't ask you to use the formula or calculate any values for polarity. I might give you some values as we are kind of here in the lecture giving a couple of values to illustrate some points. I don't expect you to use this conversion factor in any calculation. I don't expect you to use this conversion factor that tells you how much charge there is in this specific unit, or charge on an electron. But you should know conceptually that the polarity of a bond or the polarity of a molecule can be quantified, and the quantity associated with that polarity, or if something's more polar versus less polar, it will be more polar if I have greater amounts of charge, and it will be more polar if the charges are farther apart. So there are two factors that affect polarity. One is the distance between the charges, and the other is the quantity of charge. The quantity of charge involved. So let's look at some illustrations of that. Right, so here we have an example where we have chloromethane, this molecule here. The chlorine is more electronegative than the carbon. Chlorine's electronegativity is about 3, carbon's about 2.5. So it's not a huge difference, but it's definitely a significant difference. There's also no difference between hydrogen and carbon, which is 2.1 versus 2.5. And so those hydrogens are also allowing electrons to be pulled toward the carbon, and then electrons are pulled toward the chlorine. So overall, the net pull or shift in the electrons, or the induction that's occurring here, is a net overall shift up from the area that's more positive on the bottom of the structure to the area that's more negative on the top of the structure. So you could look at that quantitatively, and as we were just saying, the bigger the electronegativity difference between the atoms involved, the larger the quantity of partial charge created. So chlorine's more electronegative than carbon, but not by a lot, so maybe I only have a minimal amount of negative and positive here. That's not the only factor that affects polarity, though. Also, the distance between the partial charges that are created is important. Right? So the longer this bond is, the farther away that negative is from the positive, the greater the dipole. So that factor isn't a major factor, but it is significant, so you should at least be aware that distance is a factor here. So to calculate the dipole, or how polar this structure is, we have to multiply the quantity of charges involved by the distance between them. The greater the distance, or the greater the quantity of charge, the larger the dipole. And so again, I won't ask you to do that with actual numbers, but you should know that those both are factors that factor into how polar a structure is. And then the larger the value with units of debye, the greater the polarity of that molecule, and the more strongly it can line up its areas of partial positive and negative with other molecules to form dipole-dipole attractions, which you should know from general chemistry affects a lot of the properties. So we could also calculate what the polarity would be if there were no sharing of electrons. And so if we imagine, just for the sake of argument, that this pair of electrons weren't shared but existed only on the chlorine as a lone pair, it would have a full negative and the carbon would have a full positive. And if we calculated the dipole factoring in full charges here instead of partial charges, but kept them at the same distance, when we multiply that, we'd end up with a much larger polarity. So again, I won't ask you to calculate this value, or the value from the previous slide, that was 1.87 debye. So 1.87 debye is what we get for the covalent bond, and 8.51 is what we would get if it were an ionic bond. But knowing these two values, if I gave you both of these values, I might expect you to calculate what percent of the bond is covalent versus what percent of the bond is ionic. So the real life polarity of this molecule is 1.87, and what it would be if it were fully ionic is 8.51. So what percent of that is ionic? So to get a percent, if I ask you to calculate the percent to which a bond is ionic, that's going to be equal to the quantity of the dipole that it actually has divided by what it would be if it were fully ionic times 100. Like any percent is the part divided by the total possible. If it were fully ionic in this case, multiply it by 100. So 1.87 divided by 8.51 times 100 gives me 21.97, or about 22%. So this particular bond is only about 22% ionic, and that means it's 78% covalent, right? Which is not surprising, because if I take the electrons and put them only on the chlorine and make it ionic, then the carbon doesn't have a noble gas configuration, and it creates these unstable formal charges, especially the one on the carbon. So that's why there's only 22% ionic character there, or only partial charges instead of full charges, and the majority of that is shared over both atoms to complete both atoms' noble gas configurations and avoid the unstable full charge, especially on the carbon, that would exist if it were fully ionic. So we can say this one is mostly covalent. And then we could do that type of analysis for a variety of other types of bonds if we wanted. Again, I wouldn't expect you to determine these numbers, but if they were given to you, you could calculate to what degree the observed polarity compares to what it would be if it were fully polar or fully ionic. And you can see most of these bonds are not very ionic. Most of them are more covalent than they are ionic, and that's due to the fact that the electrons have to be shared to complete both noble gas configurations and avoid relatively unstable formal charge on relatively small atoms that would create a pretty significant charge imbalance that would be unstable. But we can look at the CO double bond and note that the CO double bond is more ionic or more polar than the CO single bond by a fair amount. And the reason for that is because the pi electrons especially are not that tightly held between the nuclei. Right? So when we look at a CO single bond, that's strictly a sigma bond. If I only have a single bond, it's always a sigma bond. It always results from head-on overlap between the respective atoms, hybridized orbitals, and I get a lot of overlap. The electrons are really stable. They get into a molecular orbital that surrounds both nuclei pretty well. And the oxygen does attract that more because it's higher in electronegativity, but not a lot more, only 10%. 10% ionic, 90% covalent, meaning 90% shared over both atoms. But when I make a double bond between two atoms, part of that is going to be a sigma bond, and that sigma bond is going to be shared pretty well over both atoms. The rest of that is a pi bond, right? So the p orbital here and the p orbital here, these atoms would have to get a little closer for those orbitals to overlap side by side. But if they do, and I just look at the pi bond only, the construct of interference, we're looking at the bonding orbital because that's the one the electrons would exist in. The construct of interference there would put electrons above and below, right in the areas of overlap between both lobed sections of the p orbitals that exist there. And since these electrons are not really that tightly held to the nuclei because they're kind of above and below the plane rather than right between the nuclei where the sigma bond is, they're more susceptible to being pulled because they're not that tightly held to the carbon. And so they can shift much more readily to the oxygen. And since the oxygen has more protons in its nucleus to attract them over there, they will go over there. And that's why I get a fair amount of extra shifting of electrons toward the oxygen, creating much larger partial charges than I would normally get just for a single bond between the atoms. So pi bonds are more easily pulled toward one atom or another through induction if the atom's more electronegative, and that creates more polar bonds for the overall structure. So conceptually or visually, if I give you a Lewis structure or a formula and you draw a Lewis structure, you should be able to determine the net overall dipole for that structure. And so to do that, you can use a vector method, but the vector method I think is a little tricky for some students. So what I prefer to do is to just start by analyzing the individual bond polarities. So chlorine's more electronegative than carbon. Not a lot, but a little. Chlorine's more electronegative than carbon. Not a lot, but a little. That puts a significant partial positive on the carbon. Carbon's more electronegative than hydrogen by an even smaller margin, so that would only involve very small amounts of charge involved. So is the carbon on net more positive or more negative? Well, since the chlorines attract electrons away from it a little bit more strongly than the hydrogens push electrons toward it, due to the electronegativity difference between carbon and chlorine being slightly greater than that between carbon and hydrogen, the carbon should have a net positive rather than a net negative. And so once I determine the individual charges on each atom, then I want to average that out. So if there are two negatives, the average negative would be right between them. And if there are three positives, the average positive would be right between them. It might be closer to the hydrogens than the carbon if the hydrogens carry a larger quantity of partial positive than the carbon. So if I can look at the electronegativity differences and say, in this case I can't really do too much, but if I could say, well, maybe there's a really large partial positive here but not over here, that would affect where the central or average position of positive is, but in this case it's going to be somewhere down here. So I can then draw an arrow from the positive to the negative to show the molecular dipole moment, or the overall net dipole of the whole structure, or alternatively I could show that net overall dipole by drawing two opposite partial charges on opposite ends. So one arrow or two charges is the appropriate way to show the net overall dipole. Looking at these structures down here, so here the nitrogen is more electronegative than hydrogen, so each one of these would carry a little bit of a partial positive and a partial negative. Oxygen is much more electronegative than hydrogen, so very large partial negative, partial positives. But if I want to show the overall net dipole on the structure, I've got to find the average position of negative, which is definitely on the nitrogen since that's the only area of negative here. And the average position of positive would be centered between those three hydrogens that are equally carrying equal amounts of positive. And then the same thing here. There's the only area of negative is on the oxygen, and the two positives on the two hydrogens balanced out to be kind of right in the middle. So one arrow or two partial charges shows which side of the molecule is negative and which side of the molecule is positive. I want to emphasize, it is really critical that you analyze the molecule's geometry first. Because if I incorrectly assess that the water's geometry is linear, then I would incorrectly start to believe that it's not polar. There's still an electronegativity difference between oxygen and hydrogen, creating a negative and positives. But in this case, if the two positives are spread out evenly on either side of the oxygen, then the average or central position of positive would be right between them, which is where the negative is, and it would cancel out and I would have no net dipole. So I would start to think that water is not polar, and that's not true. Water is obviously very polar, so I have to analyze geometry first. I have to draw the molecule as it correctly looks three-dimensionally with at least roughly the correct angles if I want to be able to determine that there's a negative end and a positive end. And that's true for any structure I might want to analyze. So this one here we talked about already. Just to point out, sometimes you'll see like this map across the surface of the molecule. So this molecule is like underneath here. This map, just a visual way of showing the same thing. So the arrow shows the carbon end is positive, the chlorine end is negative. The partial symbols show the carbon end is positive, the chlorine end is negative. And the map shows the same thing. Red always means negative, blue always means positive. This is not red and blue wave sign. It's not the mathematical sign of the wave. This is red and blue areas of charge, and green areas are kind of neutral. Right? So I've got a negative end on the chlorine end and a positive end on the hydrogen end due to the way the color looks across the map. So that's also, these pictures are nice as well because you can see kind of the whole electron cloud, right? If we just draw the Lewis structure, we don't recognize that this electron cloud is actually this big cloud surrounding, the structure three-dimensionally, and the map does a nice way of showing where the electron cloud is, as well as where there might be a little extra negative due to the more electronegative atom pulling electrons to that side. This table shows a few dipoles. You can see how the carbon-oxygen double bond creates a fairly large dipole for that structure. Here in methanol, I've got a Lewis structure that involves a big electronegativity difference between O and H, as well as a fairly large electronegativity difference between O and C. So I've got a lot of negative on one end, a lot of positive on the other, and that creates a large dipole moment as well. When the electronegativity difference isn't as big, I don't get as big of a dipole moment. The issue with water is that the hydrogen and oxygens are pretty close together. And so the separation between the positive and negative isn't as large, so I don't have as big of a dipole moment there. The pentane is an interesting example. If I look at the shape of these carbons, I really shouldn't draw it like this because it kind of makes it look like all the angles are like 90 degrees. All these carbons should have tetrahedral geometries. So the way you would want to draw that to make it look as close to what its actual shape would be is to use a zigzag, right? Any carbon-carbon bond angle between carbon-carbon bonds should be about 109, not 90 degrees. So if I put my 5 carbons at an angle and then show the hydrogens attached, that is the most atoms I can put all in the same plane. Because of the tetrahedral shape, one of the hydrogens here would be coming out at me, and the other would be pointing away, and that would be the case on every one of these carbons. So you want to also start getting used to trying to draw the structures in a way that looks three-dimensionally how they actually look in real life. And I think soon, I was meaning to do this already, but I forgot. So starting as soon as I can remember, when we get into lab, I want to loan out to each one of you a model kit so you can start to make models of these structures and see what they look like three-dimensionally, kind of check your geometries and check the way you're drawing them to make sure they look somewhat realistic, because that's really helpful, especially as we get deeper into looking at these structures three-dimensionally. So if I'm looking at the dipole here, I can notice every one of these CH bonds is slightly polar. Carbon's electronegativity is slightly higher than hydrogen. So I'm going to have negatives on every one of these carbons, but they'll be very small quantities of negative. And I'll have a partial positive on every hydrogen, just a little bit, very small quantities. If you look at this structure three-dimensionally though, and where all the positives and negatives are distributed, they all really balance out, because where's the central or average location of negative? Well, it's between all these negatives, like right in the middle. And where's the average or central position of positive? Well, it's between all the positives that are all decorated around the outside, which is also right in the middle. So when the center of positive and negative are both in the same spot, that's when you get no net dipole on the structure. Any questions about that? So then the last quiz question was about geometry and polarity. So let's just take a look at some of this. We have very little time left, but we're almost done. So this carbon here has a steric number of 2. It's got 1, 2 sigma bonds and no lone pairs, so it should be linear. The 2 pi bonds there are above and below the plane of the carbon-nitrogen sigma bond. This carbon here is bonded to 4 things. It's bonded to 3 hydrogens and another carbon. Right, so once we analyze this, it doesn't mean it's not part of the molecule. If I'm analyzing the geometry of this carbon, it's still bonded to 4 total things, so it should be tetrahedral. And so if I were to draw that three-dimensionally, I'd want to make sure that the linear carbon has the two atoms bonded to it 180 degrees apart. And I want to make sure that the tetrahedral atom has that three-dimensionality shown. And so that would involve one hydrogen being shown kind of pointing out at me, out of the plane of the screen, and one pointing back into the plane of the screen. Now I can analyze the polarity. Nitrogen's more electronegative than carbon, creates a negative. And as we were talking about a little while ago, the pi bonds are really mobile. They're not stuck right between the nuclei like the sigma bond is very much. So they can really shift over there, and that's going to create a really large partial positive here. So that's the major area of this structure that's creating polarity. The CH bonds create maybe some minimal partial charges, but they're not going to be even very relevant compared to the large partial charges here. So my polarity is going to go in that direction, and I can show it with the negative end of the arrow or the negative symbol, and then the positive end of the arrow or the positive symbol. Looking at the next structure, we'll look at the geometries of these central atoms. This carbon's bonded to 3 hydrogens and a carbon, so that's 4 total bonds, so that's tetrahedral. This carbon has a steric number of 3 sigma bonds and 1 pi, so it's going to be Sp2 hybridized, bonded to 3 individual atoms, so it's trigonal. And Sp2 hybridization is flat, so it's going to be trigonal planar. Let's talk about the geometry of the nitrogen later. This is a little more advanced than we needed to do. We'll deal with that later. So if I wanted to redraw this, I would show this carbon here as being tetrahedral with the 4 things attached to it. Only 2 of those 4 can be in the same plane. The other 2, one would be sticking out at me and one would be pointing away. This carbon is trigonal planar, so the 3 things bonded to it are all in the same plane. And then this nitrogen, we can just keep that as an NH. Actually, I should probably put those hydrogens in there so we could see the electronegativity differences. So as we were saying earlier, the carbon-oxygen electronegativity difference is a huge difference. It's going to be a very large partial negative, very large partial positive. What's happening over here isn't that relevant because the electronegativity differences are much smaller in comparison to that one. Over here, the nitrogen is a little bit more electronegative than the carbon, so that adds to how much positive is around the carbon. And the nitrogen is also pulling electrons away from the hydrogen, so that's going to be a little bit of a partial negative, partial positive, partial positive. So this is a little bit trickier, but overall I can see I've got a negative end, mostly on the oxygen, but a little bit on the nitrogen, so maybe in between there is maybe the central position of negative. Where is the average position of positive? Well, it's mostly on the carbon, but also a fair amount on these hydrogens, because the electronegativity difference between nitrogen and hydrogen is pretty big. So the negative, or the positive, might be down here, in between those 3 areas of positive. So then my arrow would go roughly in that direction. This last one, these carbons are trigonal planar. They've got 3 sigma bonds, so they're Sp2 hybridized. This carbon here and here is going to be tetrahedral, just like the other CH3 groups we looked at. In terms of the polarity, so this one's already pretty well drawn with the right shape. The CH3 groups shape isn't really that relevant because the bond polarities aren't really that polar. It's not going to affect the overall polarity too much. But the nitrogen-carbon bonds are creating some dipoles, so I have some negative on these nitrogens. That's really the only area of negative. So the central or average position of negative would be right between those nitrogens, right in the middle of the structure. And where's the positive? Well, if the nitrogen is pulling electrons away from the carbon, these carbons are a little positive. The hydrogens are a little positive, and they're kind of distributed on opposite sides of the structure. So where's the central positive? Right between the hydrogens and the carbon, which is right in the center of the structure. So here, if the average position of positive and negative are in the same spot, then I have no net dipole. I don't have opposite charges on opposite ends, and so I could label that one as being nonpolar. Alright, so here are the bullet points for what we talked about today. This is day 2, and this should not say exam 1. Apologize for that. This should say exam 2. For those of you who have not had an exam yet this week, this material won't be on your exam until next week. And here are some practice questions from the textbook that are relevant to what we just talked about, so you can kind of check your work against the practice exam, or against the solutions guide for the textbook. And then on Thursday, we're going to finish chapter 1 and get into chapter 2 a little bit. So there's some videos to help you prepare for that. And then obviously the day 3 quiz questions you should do before 1 p.m. on Thursday related to this content. And you can always reach out to me if you need help with that stuff. It seems like most groups are working pretty well together. I'm seeing a lot of chatter on the Discord chats, which is great. You all are communicating and talking about what you should be doing. There's a few people who aren't really communicating too often or too well with their groups, so I would encourage them to try to get a little bit more involved. That way you make sure that you actually helping with the group work that your group is working on. If you don't, and I don't see that you've done any work in the history of your Google Doc or been involved in discussing these concepts with your group in any way, then you won't get full credit for the quiz that your group submits. So if you want to make sure you don't miss out on those points, you want to be active in your Google Docs and in the Discord chat. So any questions about anything before we end for today?
I don't know if this is a fair question to ask, but aside from the practice problems, what else do you recommend we do to prepare for quizzes?
Prepare for the quizzes?
Yeah.
So to prepare for the quizzes,
Class quizzes, I mean.
the what?
The in-class quizzes.
Oh yeah, so I'm calling those exams just to try to keep them differentiated. But yeah, for the exams, now that we're starting to have quizzes, so when we have exam 2 next week, the feedback I give you on your quizzes that relate to the day 2 and day 3 material will be relevant to those exams. So in general, the feedback I give you on the quizzes, the textbook reading, the practice problems that are in the textbook, the videos, and then if you get through all of that and you want more practice, the practice exams are pretty good, although they don't really show effectively which problems are from which day's material. So I should really, I wish I had more time over the summer to go through there and designate which practice problems on the practice exam relate to which material. But you can always ask me that. You can always ask me about that. So if you want to work on the practice exam, you want to try to focus on what to expect for exam 1 or exam 2 or a specific exam, you could always say, hey, is this question on the practice exam relevant to the exam we're going to have coming up? That would also be a place for you to find practice problems. But what's in the textbook is pretty good at covering a lot of the bases. But between all of that, I think you should be in pretty good shape, especially since each individual exam isn't covering that much material. Any other questions about anything?